This example shows the practical or implementable power architecture based on battery dominant power architecture that accommodate uniform voltage distribution maximum power tracking control. In this architecture, all three sourcing voltages V1, V2 and V3 are controlled to have uniform distribution. The bus voltage V bus is the voltage across the battery dominant voltage bus, and I bus is the total sourcing current from the dipole converters. Another feedback variable is I bat, which is the battery charging current. This is a system controller for the battery dominant power architecture that's shown in the previous slide. This architecture accommodates uniform voltage distribution, maximum power tracking. Distributed input voltage V1, V2 and V3 are fed back for achieving their equal sourcing voltages. The bus voltage V bus and the battery charging current I bat is controlled or regulated by battery charge controller. Under such a circumstance, the diode D always forwards bias. When the battery charge controller fails to regulate the I bus or V bus to the target, the diode D will be reverse bias, and the primary control voltage VC is controlled by the maximum power tracking controller that working together with the input voltage regulator. In this manner, the sourcing voltage V1 is regulated to the value corresponding to the set point voltage VSP, which is the peak power voltage candidate generated by maximum power tracking controller. The sourcing I bus current and the sourcing voltage V1 are the necessary input signal for proper processing direction towards the peak power by the MPT controller. Another architecture that also implementable is called bus regulated power architecture with uniform voltage distribution maximum power tracking control. In this particular architecture, bus load voltage Vout is regulated while keeping equal sourcing voltages across power source number 1, power source number 2 and power source number 3. I bus and V1 are used by MPT control to track the system optimum power. This slide shows the system controller block diagram for regulated bus power architecture. Battery current and voltage, which is I bus and V bus, are used for battery charge control to safely maintain the battery health. When the battery charge controller fails to do its regular function, the system automatically transits to maximum power tracking mode. In this mode, the sourcing voltage, the maximum value of the sourcing voltage that select from either V1, V2 or V3 is regulated at the value corresponding to the peak power set point voltage VSP. VSP is the peak power point voltage candidate generated by MPT controller that using two signals. One signal is total sourcing current I bus and the other signal is AC distor signal V distor. V distor is a sinusoidal of low frequency that generated internally by the MPT controller. Usually, V distor have the same AC voltage ripple across sourcing voltage V1, V2 or V3. In this manner, there is no need to have the direct feedback from the sourcing voltage from V1, V2 or V3 to the MPT controller. Only V distor signal is already become the representative, providing the AC ripple voltage information. In this manner, only one feedback variable from I bus is necessary, where the distor signal is just the internal control signal used in a maximum power tracking controller. In this manner, the feedback voltage due to V1, V2 or V3 do not need to feed directly to the MPT control and allow the control to provide the direction toward the peak power point without the switching noise that can corrupt the MPT controller fidelity. The output voltage regulator also add into this system controller to regulate the system output voltage V out to the target corresponding to V left. The control voltage VC4 directly feed the control port of the converter number 4 shown in the previous slide, and this particular converter provide the bus voltage regulation or the system voltage regulation V out. This slide shows the simulation of the battery dominant power system. On the plot, the upper plot shows the sourcing voltages V1, V2, V3 that are always equal. This simulation shows the transition between maximum power tracking mode to non-maximum power tracking mode. During the maximum power tracking mode, the sourcing voltage have the optimum power voltage around 32 volts with a low frequency AC ripple of about 20 Hz superimposed on the sourcing voltage, signifying that the system is in maximum power tracking mode. In this mode, the battery current is charged at the maximum rate as the power system can offer. Since the battery controller already loses regulation because its charging command already set significantly high above 53 amp. As soon as the charge command of the battery controller reduces the charge command to 50 amp, the battery charge controller is able to restore its control and cause the maximum power tracking mode to be in standby mode. In this mode, the active battery current regulation happens at 50 amps and the sourcing voltage no longer has the 20 Hz AC ripple. This slide shows the similar simulation of the battery dominated power system, emphasizing the operation in maximum power tracking mode when the sourcing voltage settle at around 32 volts with 0.5 volts peak-to-peak ripple of 20 Hz digital signal superimposed on 32 volt DC. In this mode of operation, the battery current is charged at 53.6 amp, which is the maximum current battery that the power system can offer to charge the battery. Despite the fact that the battery charge controller already command the battery to charge much higher commanding charge rate far above 53 amp. However, the system peak power can only accommodate at 53.6 amp as the battery charge current. The sourcing voltage remain uniformly distributed or equal.